Welcome back. We're going to finish our discussion on hydrogen bonding with this information. And if you notice, you can see a graph on the screen, right? Now, what they have done here is they have taken hydrogen and mixed it with all elements in each of the four columns in the periodic table, such as group 4, group 5, group 6, group 7. And then they determined the boiling point for each of those compounds, and then they drew a graph, right? So your y-axis is the temperature, which is actually the boiling point temperature, and then the x-axis is your column or the group where the elements are found, right? So let me write a generalized statement, which is typically, okay, larger the molecule, that is, if you calculate the molar mass, then you can determine whether it's large or small compared to another molecule. Typically, larger the molecule, the higher the boiling point temperature. The higher the boiling point. Now, this is a generalized statement and it works in most of the case. So, for instance, if you take group 4, which is the carbon family, you got CH4, you got silane, you got germanium, molecule, and then you got the tin, right? Now, if you notice, this statement seems to work in this case, right? You got, this is the biggest of the four, and clearly this has the highest boiling point of them, right? This is the lowest, and this is the highest. But that trend falls apart as soon as we go to group 5, 6, and 7. In group 5 is your nitrogen family, and all they did is they combined nitrogen with hydrogen, phosphorus with hydrogen, and then arsenic with hydrogen, and then antimony with hydrogen, right? Now, there may be a little bit of fluctuations between groups, but within a group, you see that these three seem to follow the trend, whereas the nitrogen falls out of place, right? Nitrogen, in fact, has a higher boiling point, even though its molar mass. Ammonia is only about 17 grams per mole, and phosphine is 34 grams per mole. So clearly, phosphine should have a higher boiling point than ammonia, but that's usually not the case. You see that ammonia has a higher boiling point than phosphine, right? So that's because nitrogen is directly attached. If you draw the structures like you learned in Chem 170, you see that this is how it looks like, right? And this is a polar molecule, obviously, and it also contains hydrogen bonding because the hydrogen is directly attached to the nitrogen, right? So that's why, which is not the case in phosphine, because like I said, for hydrogen bonding to happen, the oxygen must be attached to the hydrogen, the nitrogen must be attached to the hydrogen, or the fluorine must be directly attached to hydrogen. And you can see the same trend across the other groups, such as group 6 and 7. Now you would wonder, if I said that typically compounds containing nitrogen, hydrogen, oxygen, hydrogen, and fluorine, hydrogen, and I said this would be typically this is the lowest, this is the highest, right? But you see that water has a higher boiling point compared to HF, even though they both have hydrogen bonding. But that is primarily because water has two active sites for hydrogen bonding, whereas hydrogen fluoride has only one vacant spot, right? One hydrogen bonding site compared to water, and that's why water is a little bit higher than fluorine. This is an exception, but this is the only time you're going to see this. So similarly, in group 6, you see all these molecules are bigger compared to water, but water wins the race with the boiling point because only water can have hydrogen bonding, and the same with hydrogen fluoride, right? So When I give you a compound and I ask you to determine which of the following compounds has the highest boiling point, first you have to determine whether the hydrogen is directly attached to the oxygen. Is it directly attached to the hydrogen? Is it directly attached to fluorine? If it is not, that molecule doesn't even contain hydrogen bonding, like I showed with acetone. Okay, so and then you determine, say if a molecule contains 2 OHs and then some contains 3, some contains 1, some contains 4, then the more the OH bonds, the more the boiling point would be. That means it boils at a higher temperature, right? For instance, if I take methanol versus glycerol, okay, which I showed the structure earlier, methanol, which contains only 1 OH, right? Whereas glycerol contains 3 OHs. So if you compare these two, this would boil at a higher temperature because this contains 3 hydrogen bonding sites, whereas this contains only 1 hydrogen bonding site. And this is important because the next item I'm going to talk to you about is ion-dipole interaction. And now that we have understood what a dipole is, and we already know what an ion looks like, something that has a positive or negative charge, and how does that result in a higher boiling point. Hopefully by the time I finish the ion-dipole interaction, you can probably answer one of the major questions I've posted at the beginning of this topic on molecular forces. All right, so stay tuned. I'll be back with ion-dipole interaction and then ionic bonding. All right.